The morning of February 3rd, 1943, a sergeant named Roy Dunlap stood in the armory tent at Henderson Field on Guadalcanal, staring at a problem that threatened to kill American pilots. Scattered across his workbench were the disassembled components of 6 Browning M2 aircraft machine guns, each one pulled from different fighters after jamming during combat sorties over the Solomon Islands. The guns had failed at the worst possible moments during diving attacks on Japanese bombers in the middle of strafing runs against enemy positions, while engaging Zero fighters at close range. Pilots were coming back furious, shaken, sometimes not coming back at all. Dunlap was not an ordinary armourer. Before the war, he had worked as a gunsmith in Oklahoma, spending his days accurizing hunting rifles and repairing shotguns for farmers. He understood firearms the way a master mechanic understands engines, not just how they worked, but why they worked, and more importantly, why they sometimes didn't. The Army had recognized this expertise and assigned him to the Armory section of the Marine Air Group 23, where his unofficial job description had become "fix things that aren't supposed to be fixable." If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem in front of him was maddeningly simple in its presentation, but devastatingly complex in its implications. The M2 Browning, that legendary 50 caliber heavy machine gun designed by John Moses Browning near the end of the First World War, was supposed to be one of the most reliable weapons in the American arsenal. On the ground, mounted on tripods or vehicles, the gun performed magnificently. Soldiers loved it. It could fire for hours with minimal maintenance, punching through armor and fortifications with brutal efficiency. The weapon had earned its nickname Deuce through years of faithful service, and by 1943 it had become as iconic as the soldiers who wielded it. But the aircraft version was different. The M2, as it was officially designated, had been lightened and modified for installation in fighters and bombers. Engineers had reduced the barrel weight, increased the rate of fire to between 700 and 800 rounds per minute, and adapted the feed mechanism for the violent environment of aerial combat. The gun needed to function while pulling multiple G-forces during tight turns, while the aircraft shook from engine vibration, while diving at speeds exceeding 300 miles per hour, and while subjected to the extreme cold of high-altitude flight. Under these conditions, the guns were jamming, not occasionally, not rarely, but with alarming frequency that was getting men killed. Dunlap had spent the previous week documenting every failure. He had interviewed pilots, examined spent cartridges, measured feed angles, and studied the wear patterns on feed mechanisms. He had fired the guns himself on the test range, watching carefully as belts of 50 caliber ammunition fed through the mechanisms. And he had identified the source of the problem, though the solution remained elusive. The issue centered on the belt feed system, specifically on how the metallic link belts flexed and twisted as they entered the gun's feed mechanism during the violent maneuvers of air combat. To understand why this problem mattered so profoundly, one must understand what the M2 Browning represented in American military doctrine and what was at stake in the skies over the Pacific in early 1943. The 50 caliber machine gun had become the standard armament for American fighter aircraft, a decision that reflected both engineering pragmatism and tactical philosophy. When war erupted in December 1941, the United States found itself facing enemies equipped with various calibers of aircraft, weapons, from rifle-caliber machine guns to 20mm cannons. The Germans favored cannons for their fighters, mounting 20mm and even 30mm weapons that could destroy an aircraft with just a few hits. The Japanese used a mixture of rifle-caliber weapons and 20mm cannons on their fighters. Both approaches had merit. Cannons delivered devastating explosive power but carried limited ammunition and had slower rates of fire. American planners had chosen a different path, selecting the 50 caliber Browning as the primary fighter armament. This decision was not arbitrary. The 50 caliber round offered several crucial advantages. It provided significantly more hitting power than rifle-caliber weapons, The half-inch diameter bullet weighed over 700 grains and could penetrate armor plate at combat ranges. The armor-piercing incendiary rounds could punch through engine blocks, fuel tanks, and structural members with devastating effect. The weapon's rate of fire, between 700 and 800 rounds per minute per gun, meant that a fighter equipped with 6 M2s could put 4,800 rounds per minute into the air, a density of fire that could soar through enemy aircraft. Most American fighters carried between 6 and 8 M2 machine guns. The Republic P-47 Thunderbolt mounted 8 guns, 4 in each wing. The North American P-51 Mustang carried 6. The Vought F4U Corsair, which was just beginning to see service in the Pacific, also carried 6. Each gun was fed by a belt containing between 300 and 400 rounds, giving pilots between 20 and 30 seconds of total firing time before their ammunition ran out. This ammunition capacity was critical. In the brief, violent encounters that characterized air combat, pilots had only seconds to line up their targets and fire. A fighter making a high-speed pass on an enemy bomber might have his target in his sights for less than 3 seconds. During that window, every gun needed to fire continuously and reliably. A single jam could mean the difference between a kill and a miss, between coming home safely and getting shot down by an enemy you couldn't destroy. The M2's reliability on the ground had created expectations that proved difficult to meet in the air. Ground-mounted guns operated in relatively stable environments. The weapon remained level, the ammunition belt fed smoothly from a fixed position, and the gunner could observe and immediately correct any feeding problems. Aircraft installations were brutally different. In the aircraft, the M2 was installed in the wings, sometimes angled slightly to converge the fire pattern at a specific distance ahead of the fighter. The ammunition belts were stored in boxes or channels within the wing structure, often requiring the belt to make sharp bends before entering the gun's feed mechanism. When the pilot pulled high-G maneuvers, tight turns, steep climbs, sudden dives, the belts experienced forces that tried to pull them in different directions. The metallic links that held the individual cartridges together needed to be flexible enough to navigate these bends and twists, yet rigid enough to feed reliably into the gun's mechanism. The standard M1 link, adopted in 1940, had been designed primarily for ground use. Each link was a small piece of stamped steel that held a single cartridge, connecting to the links on either side through a simple pivot mechanism. When thousands of these links were assembled into a belt, they created a flexible chain that could bend in 2 dimensions up and down, and side to side. This flexibility worked well for ground guns, where the belt fed in a relatively straight line from an ammunition box positioned beside the weapon. Aircraft installations demanded more. The belts often had to make 90-degree turns, sometimes in multiple directions, as they traveled from the ammunition storage to the gun. During violent maneuvers, the belts twisted, and this torsional stress, the tendency of the belt to rotate along its length, caused problems. The links would bind against each other, creating friction that resisted the gun's feeding mechanism. Sometimes the links would twist enough that the next round would not align properly with the feed mechanism, causing the gun to jam. By early 1943, the problem had become serious enough that the Army Air Forces had requested a redesign. The result was the M2 link, adopted in February 1941. This new link featured a revised geometry with tapered sides on the center loop and slightly more rounded connecting ears. The center loop was marginally larger in diameter than the M1 link, providing more clearance as rounds fed through. These changes nearly doubled the belt's flexibility compared to the earlier M1 design. But doubling flexibility was not enough. Pilots were still experiencing jams at rates that concerned squadron commanders and frustrated the men whose lives depended on their guns. The official reliability standard called for no more than 1 malfunction per 4,000 rounds fired. In practice, under the stress of actual combat conditions, guns were jamming far more frequently. Some aircraft were returning from missions with 2 or 3 guns jammed out of 6. A few unlucky pilots had experienced total failures, all their guns jamming simultaneously, leaving them defenseless against enemy aircraft. This was the situation that Roy Dunlap confronted in that armory tent on Guadalcanal. He had the modified M2 Lynx. He had properly maintained guns. He had ammunition that passed all inspections. Yet the failures continued, and men were dying because their weapons would not fire when they needed them most. The official channels had done what they could, redesigned the Lynx, issued technical bulletins, trained armourers in proper installation and maintenance procedures. But none of it was enough. Sergeant Roy Dunlap had been trained at the Army's Ordnance School at Aberdeen Proving Ground in Maryland, where instructors drilled into every armourer the sacred principle that proper maintenance and correct procedure would solve any mechanical problem. The curriculum emphasized field manuals, technical specifications, and adherence to official guidance. Students learned to disassemble and reassemble the M2 Browning blindfolded. They memorized headspace and timing procedures. They studied the metallurgy of barrels and the chemistry of different lubricants. The message was clear and consistent. Follow the manual, and the weapon will function. But Dunlap's background as a civilian gunsmith had taught him something the Army didn't emphasize, that sometimes the manual was wrong, or more precisely, that sometimes the manual addressed a different problem than the one you faced in the field. On Guadalcanal, he had access to tools that most forward armourers lacked. He had micrometers for precise measurement, gauges for checking tolerances, and a small lathe for fabricating custom parts. More importantly, he had the intellectual freedom that came from understanding principles rather than just procedures. He began his investigation by examining the physics of the feed mechanism. The M2 Browning fed ammunition through a complex sequence of movements. As the gun fired, the recoiling barrel and bolt assembly moved backward together for a short distance. This rearward motion was arrested when the barrel reached its rearmost position and stopped. The bolt, however, continued moving backward, unlocking from the barrel and travelling further to the rear of the receiver. As the bolt moved backward, it cammed against the belt feed slide, pulling it to one side. This sideways motion of the feed slide grabbed the metallic link belt and pulled it through the feed mechanism, positioning the next cartridge in line to be stripped from the belt and chambered. The entire sequence happened in a fraction of a second. At 700 rounds per minute, each complete cycle, firing, extraction, feeding, chambering, and locking, took approximately 86 thousandths of a second. During this brief interval, the belt had to move smoothly through the feed throat. The next cartridge had to align perfectly with the chamber, and the link holding that cartridge had to separate cleanly from the belt. Any disruption in this sequence caused a malfunction. Dunlap observed that jams occurred most frequently when the ammunition belt had to make sharp bends before entering the gun. He measured the angles in typical wing installations and found that belts often had to navigate turns of 80 to 90 degrees in the horizontal plane, combined with additional vertical bends. When the aircraft maneuvered violently, the ammunition in the storage boxes experienced accelerations that could reach 4 or 5 times the force of gravity. These forces tried to keep ammunition moving in its original direction, creating resistance as the belt was pulled through the bends and into the gun. He conducted a test, firing a gun on the ground while manually inducing tension on the belt to simulate the resistance that would occur during flight. The gun jammed after approximately 200 rounds. He reduced the tension slightly and tried again. This time the gun fired nearly 400 rounds before jamming. He documented these results carefully, noting that even modest amounts of tension on the belt dramatically increased the likelihood of malfunctions. The problem was becoming clear. The M2 link had been designed to provide flexibility in bending, allowing the belt to navigate curves in the ammunition feed path. But flexibility in bending was not the same as resistance to twisting. When tension pulled on the belt during maneuvers, the individual links twisted relative to each other, changing the angle at which cartridges entered the feed mechanism. This twist was subtle, perhaps only a few degrees, but at the violent speeds of the gun's operation, even small misalignments caused failures. Standard Army procedure called for careful routing of the ammunition belt to minimize sharp bends, proper lubrication of the links to reduce friction, and regular inspection of the feed mechanism for wear. Dunlap had followed all these procedures. Every gun that failed had been properly maintained, correctly installed, and fed with belts that passed all inspections. The problem was not maintenance or procedure. The problem was that the design, optimized for ground use, was being pushed beyond its limits by the demands of aerial combat. On February 8, 1943, Dunlap had what he would later describe as his moment of clarity. He was examining a jammed gun that had been pulled from a Wildcat fighter after a mission over New Georgia. The pilot reported that all 4 of his guns had jammed within seconds of each other during a diving attack on a Japanese transport ship. The gun in front of Dunlap had a cartridge stuck halfway into the chamber, with the belt twisted at an odd angle behind it. As he carefully extracted the jammed round and examined the belt, he noticed something. The metallic links were not just twisted, they had formed a slight spiral pattern, like a gentle corkscrew, in the section just before the feed throat. This spiraling had caused each successive cartridge to enter the feed mechanism at a progressively worse angle, until finally one had wedged itself at such a severe angle that the gun could not chamber it. He sat back and considered the problem from first principles. The belt needed to be flexible enough to navigate the bends in the ammunition feed path, but it also needed to resist twisting under tension. These were competing requirements. More flexibility generally meant less resistance to twisting. The M2 link represented the Army's best compromise between these demands, but compromise was not enough. What if, Dunlap thought, the problem was not the individual links, but how they connected to each other? What if he could modify the belt to physically prevent that spiraling motion? He spent the next 2 days experimenting. His first attempt involved adding small washers between links to increase the spacing, theorizing that more space might reduce binding. The modification showed modest improvement but introduced new problems. The increased spacing made the belt longer, requiring modifications to ammunition storage that were impractical for field implementation. His second attempt was more promising. He took a standard belt and carefully bent small tabs on alternating links, creating physical stops that prevented the belt from twisting beyond a certain angle. He test-fired this modified belt and immediately noticed smoother feeding. The gun fired 600 rounds without a single malfunction, far better than the typical performance with standard belts. But the hand-modified tabs were crude and time-consuming to produce. He needed something that could be fabricated quickly and installed by any armorer in the field. For 3 more days, he worked through different designs, fabricating small clips and guides from scrap metal, testing each iteration, refining the concept. On February 13th, he assembled his most promising design. Using thin strips of spring steel salvaged from damaged equipment, he fabricated small clips that attached to the belt at regular intervals. Each clip engaged with adjacent links in a way that allowed the belt to bend normally but prevented it from twisting. The clips were simple, just bent pieces of metal, but they transformed the belt's behavior. The belt could still navigate the sharp bends required by aircraft installations, but it could no longer spiral under tension. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. He loaded this modified belt into a gun and began firing. 100 rounds fired without issue, 200 rounds, 500 rounds. The belt feeding was noticeably smoother, the sound of the guns cycling more regular. At 1,000 rounds, he stopped to inspect the gun and the belt. Everything looked perfect. He resumed firing. 1,500 rounds, 2,000 rounds. The barrel was glowing red-hot, but the gun continued to function flawlessly. At 2,500 rounds, he was running low on ammunition. He had already exceeded any reasonable combat scenario. No pilot would ever fire this many continuous rounds in actual combat, but he wanted to know the absolute limit of what his modification could achieve. He sent a runner to collect more ammunition from the main depot. While waiting for more ammunition, Dunlap carefully examined the gun and the belt. The barrel was too hot to touch and would need replacement soon, but the feed mechanism showed no signs of unusual wear. The metallic links were still properly aligned, the spring steel clips were intact, and there was no evidence of the spiraling that had plagued standard belts. Other armourers had gathered to watch the test, curious about the extended firing that was producing a near-constant roar from the test range. When the ammunition arrived, Dunlap resumed firing. 2,600 rounds, 2,700 rounds. The gun's cyclic rate had slowed slightly as metal expanded from heat, but it continued to function. At 2,800 rounds, he paused again. The barrel was beyond its recommended service life, glowing orange in the tropical afternoon sun. By every technical standard, he should stop the test, replace the barrel, and write up his results. But something drove him to continue. Perhaps it was the memory of pilots' faces when they described their guns jamming during combat. Perhaps it was the satisfaction of solving a problem that official channels had failed to fix. Perhaps it was simply the craftsman's desire to see how far his creation could go. He fired the remaining ammunition in controlled bursts, managing the barrel's temperature to avoid catastrophic failure. At 2,850 rounds, the ammunition belt ran dry. The gun had fired continuously, with Dunlap's modifications in place, without a single malfunction. 2,850 rounds, without jamming more than 7 times the official reliability standard, and far beyond what any pilot would fire in a single combat engagement. Dunlap unloaded the weapon and allowed it to cool. The barrel was ruined, its rifling fire-cracked and throat eroded beyond acceptable limits. But the feed mechanism and his belt modification had survived intact. More importantly, he had proved that the concept worked. The simple addition of spring steel clips to prevent belt twisting had transformed the M2's reliability in aircraft installations. Word of the test spread quickly through the aviation units on Guadalcanal. Within days, pilots were asking when their guns would receive the modification. Within weeks, other armourers were fabricating their own versions of Dunlap's clips, adapting the basic concept to their available materials and tools. The modification required no official approval, no changes to tech manuals, no procurement of specialised parts. Any competent armourer could make the clips from scrap metal in less than an hour. The impact was immediate and dramatic. Squadron maintenance logs began showing sharp decreases in weapon malfunctions. Pilots reported that their guns were firing complete bursts without jamming. Mission effectiveness improved, as fighters could engage targets with confidence that their weapons would function throughout the engagement. The psychological effect was perhaps as important as the mechanical improvement. Pilots no longer approached combat with the nagging fear that their primary weapons might fail at the critical moment. By April 1943, Dunlap's modification had spread throughout Marine air groups in the Solomon Islands. By June, it had reached Army Air Forces units in New Guinea. Armourers shared the design informally, passing along sketches and sample clips, each adding their own refinements to the basic concept. Some used different materials, phosphor bronze instead of spring steel. Some changed the spacing of the clips along the belt, but all versions shared the core principle that Dunlap had discovered: preventing the belt from twisting dramatically, improved feeding reliability. The official military bureaucracy took notice of Dunlap's modification, though not in the way one might expect. In August 1943, an Ordnance Technical Bulletin was issued from the Army Air Forces Materiel Command, acknowledging that field-expedient modifications to ammunition belt feed systems have shown promising results in reducing weapon malfunctions. The bulletin stopped, short of officially adopting Dunlap's design as standard procedure, but it authorized armourers to implement similar modifications at their discretion, provided they documented their methods and results. This cautious endorsement reflected the complex reality of military innovation during wartime. The modification worked, and commanders in the field wanted it implemented immediately on all aircraft. But the ordnance establishment faced legitimate concerns about standardization and quality control. Dunlap's clips were hand-fabricated from scrap materials with no two exactly alike. What worked on Guadalcanal might not work identically at other bases where different materials or slightly different fabrication methods were used. The military supply system was designed to deliver standardized parts to units worldwide, and Dunlap's modification existed outside that system entirely. Nevertheless, the modification spread through informal channels far faster than any official procurement the process could have achieved. Armourers arriving at new postings brought the knowledge with them. Maintenance personnel rotated between units and shared the technique. By the end of 1943, some version of anti-twist belt clips was in use at virtually every American airbase in the Pacific Theater. The European theater adopted similar modifications somewhat more slowly, but by spring 1944, many units operating over Germany were using modified belts. Dunlap himself remained at Guadalcanal through most of 1943, continuing his work as an armourer and developing other field modifications to improve weapon reliability. He received a commendation for his technical innovations, but no formal recognition beyond that. The military was not particularly interested in publicizing the story of how an enlisted man had solved a problem that official engineering channels had failed to address adequately. Such acknowledgement would raise uncomfortable questions about why the problem had existed in the first place and why it had taken field improvisation rather than systematic engineering to solve it. After the war, Dunlap returned to civilian life and eventually wrote several books about gunsmithing and firearms, including detailed memoirs of his wartime service. In these writings, he reflected on the peculiar nature of military innovation during wartime. The M2 Browning was an excellent weapon, designed by one of history's greatest firearms inventors and manufactured to exacting specifications. The problem was not bad design or poor manufacturing, it was that the weapon was being used in ways its designers had never fully anticipated. The aircraft installation of the M2 presented challenges that ground mounting did not. The engineers who designed the M2 link had made it more flexible than the earlier M1 link, and that improvement was real and measurable. But flexibility in bending was not the same as resistance to torsional stress, and the design process had not adequately accounted for the twisting forces that would occur when belts were pulled through sharp bends under the acceleration loads of aerial combat. Dunlap's contribution was not inventing new technology or discovering unknown principles of physics. His contribution was recognizing that the problem could not be solved within the existing framework of proper procedure and maintenance. He understood that sometimes you needed to modify the equipment itself, not just how you used it. This perspective came naturally to him as a civilian craftsman, but was foreign to military culture, which emphasized standardization and adherence to approved methods. The story of Dunlap's modification illuminates a larger truth about how American forces fought and won the Second World War. The United States did not win primarily through superior individual weapons or brilliant strategic innovation. American firearms were generally good but not exceptional. The M1 Garand was an excellent rifle, but German and Soviet rifles were adequate for their purposes. American tanks were reliable but undergunned compared to German heavy armor. American aircraft were effective, but not dramatically superior to their opponents in one-on-one performance. What set American forces apart was their ability to identify problems in the field and solve them quickly through a combination of industrial capacity, technical expertise, and pragmatic improvisation. The military establishment provided standardized equipment and procedures, but it also implicitly accepted that field modifications would be necessary and even encouraged when they improved combat effectiveness. This flexibility was built into the American military culture in ways that were less common in other armies. The German military, for instance, emphasized precision engineering and adherence to design specifications. When German weapons encountered problems in the field, the typical response was to send the issue back to the designers for a proper solution that would then be manufactured and distributed through official channels. This process produced excellent solutions but took time. The Soviet military took a different approach, accepting rougher manufacturing standards but producing weapons in such overwhelming quantities that reliability issues could be partially offset by sheer numbers. The American approach fell between these extremes. Equipment was manufactured to high standards and distributed through sophisticated supply chains, but field personnel were empowered to modify that equipment when combat conditions demanded it. An armorer like Dunlap could identify a problem, develop a solution, implement it immediately, and share it with other units without waiting for official approval. This decentralized innovation happened at every level of the American military throughout the war. Consider the numbers involved. By the end of the war, American factories had produced approximately 2 million Browning M2 machine guns in all variants. The aircraft version, the AN M2, accounted for perhaps half that total. If we assume that even a small percentage of those weapons, say 10%, experienced jamming problems that were solved or reduced by field modifications like Dunlap's, we are talking about 100,000 weapons that became more reliable through informal innovation. Each of those weapons was mounted on an aircraft flown by a pilot whose life might depend on that weapon functioning when needed. The modification itself was absurdly simple, bent pieces of metal attached to ammunition belts. The total material cost was negligible, perhaps a few cents per belt in scrap metal that would have been discarded anyway. The labor required was modest, an hour or less of an armorer's time to fabricate and install the clips. Yet this simple modification potentially saved lives and improved combat effectiveness across thousands of aircraft over 2 years of intensive combat operations. It is impossible to calculate precisely how many pilots survived because their guns did not jam at critical moments, or how many enemy aircraft were shot down by weapons that would have jammed without the modification. The effects cascaded through the air war in ways that cannot be quantified. What can be stated with certainty is that weapon reliability improved dramatically in units that adopted the modification, and that this improvement was noticed and valued by the pilots who depended on those weapons. The broader lesson extends beyond one modification to one weapon system. Throughout the Pacific War, American forces faced environments and combat conditions that designers and planners had not fully anticipated. Jungle warfare in New Guinea and the Solomon Islands imposed demands on equipment that were different from what had been expected. Naval aviation operations from carrier decks required modifications to aircraft and weapons. Amphibious assaults on defended islands needed innovations in fire support and logistics. In each case, American forces solved problems through a combination of official engineering development and unofficial field improvisation. The official channels produced important advances, improved radar, better armor, more powerful engines, more effective ammunition. But the unofficial innovations, the field modifications made by sergeants and corporals and petty officers, were equally important to combat effectiveness. These innovations spread through informal networks, shared between units, refined through trial and error, and eventually sometimes adopted into official specifications. The M2 Browning itself exemplifies this pattern. The weapon served throughout the Second World War, the Korean War, the Vietnam War, and continues in service today, more than a century after John Browning began its design. Over those decades, the basic mechanism has remained largely unchanged, but countless small modifications and improvements have been made. Some were official engineering developments, others began as field modifications that proved their worth in combat and were eventually standardized. Dunlap's anti-twist belt clips never became an official part of the M2 system in their original form. By the time the war ended, improved link designs had been developed that incorporated principles similar to what Dunlap had discovered: better resistance to torsional stress while maintaining flexibility in bending. These improved links went through proper engineering development, were manufactured to precise specifications, and were distributed through official supply channels. They worked better than Dunlap's improvised clips, as they should have given the resources devoted to their development. But Dunlap's clips had done their job when they were needed, during the critical months of 1943 and 1944, when the air war in the Pacific hung in balance. They kept guns firing when official solutions were still being developed. They gave pilots confidence in their weapons during the desperate fighting for the Solomon Islands, New Guinea, and the Marianas. They represented the kind of practical, immediate problem-solving that characterized American forces at their best. Roy Dunlap died in 1984, largely forgotten except by firearms enthusiasts who knew his writings on gunsmithing. He never received significant recognition for his wartime innovations. No medals were awarded for solving ammunition feed problems. No official histories recorded his contribution in detail. He was one of thousands of technically skilled enlisted men who made the American war effort more effective through expertise and initiative that went largely unrecognized. Yet the impact of what he did that week in February 1943 rippled through the war in ways both profound and impossible to measure precisely. Pilots flew missions with greater confidence. Guns fired when they needed to fire. Problems that had seemed intractable were solved not through brilliant engineering breakthroughs, but through careful observation, methodical testing, and practical craftsmanship. The story began with a sergeant staring at disassembled machine guns in an armory tent on Guadalcanal, trying to solve a problem that was getting pilots killed. It ended with a simple modification: bent pieces of metal attached to ammunition belts that made those guns dramatically more reliable. 2,850 rounds without jamming, 7 times the official reliability standard. Far beyond what any pilot would fire in combat, but proof of concept that the problem had been solved. That is the legacy. Not glory or recognition, but guns that worked when they were needed, pilots who came home alive, and a war effort made marginally more effective through the accumulated weight of countless small innovations. The .50 caliber Browning had always been a formidable weapon. Dunlap's contribution was ensuring it could deliver that firepower reliably under the brutal conditions of aerial combat. Sometimes winning a war comes down to details exactly that mundane and exactly that critical. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.